Okay. So not last week, on Sunday was kind of weird, right? We were drifting from one thing that we wanted to discuss to another, which is okay, I guess. But one observation that I think was clear is that the activity of neurons in the brain is irregular. Perhaps I should be more precise and say that firing rate in the cortex is rather irregular. And what we would like to understand is how this irregularity emerges. So this would be the topic of today and the next and next week. But before that, we need a language that will allow us to quantify this irregularity in the brain. And so we will start today with discussing some issues in introducing some concepts that will be later useful. So the first one would be point process. So the idea is that we are interested in the timing of events. So an event can be an action potential, but it can be the arrival of a bus or the timing of a phone call or many events, the timing of events. And we will restrict ourselves to events in which only one event can happen at any point in time. Okay? So at any point in time, there can either be an event or there can be no event. And so the first thing to introduce would be a rate. So the rate, we'll introduce a rate of events. And the rate of event is defined such that the number of events will be equal numbers of events in the interval T1 and T2 is an integral of this function from T1 to T2 lambda t dt. Okay? And lambda t will be just the sum of delta functions on the times of the events.
What is the lambda t?
That would be the rate. It would be the rate. Instantaneous rate. So the rate at time t. So we are interested in stochastic processes, stochastic point processes. And the question is, how are we going to interpret something like the average? the average of lambda t. So let's think about it in the framework of action potentials. So we have one experiment, and we have this raster plot, and we have another experiment with a different raster plot, and so on. This would be time. So what would be the rate at this time t?
The number of events divided by this total time.
But 1 point. Probability.
Yeah.
Probably taking some limits, like making the time interval less or everything over smaller. So not some PDF function maybe.
I'm sorry?
Some
This would be the experiment.
You're asking what will be the average rate of the...
What would be what's the interpretation of the average of lambda t, time t, the average of the rate?
Why do you think that the number of events divided by time?
There's only one event.
Well,
Only one event.
in general, there will be no events.
Oh, I thought for the entire interval of time. Okay.
So the idea is basically that we take, let's use a different color. So we take an interval around t, and this interval would be of size, let's call it dt. So we'll take the limit of dt goes to 0, and the limit of number of experiments going to infinity, and we will look at the number of events at interval t minus dt over 2 to t plus dt over 2 divided by dt and divided by n. So this would be a limit. So thinking about the average, this will have a limit. We need to take the limit. At. So we're looking at the number of events taking place in this interval. Yeah, at the interval.
So this is the definition of lambda t, not the average of lambda t.
No, this is average over experiments.
Yeah.
So this is the instantaneous rate in one realization. This would be the ensemble average. This would be the ensemble average of this lambda. Okay. That's one way of thinking about point processes. But there is a complementary way. Yes, sorry. This is not a Kronecker delta. This is a Dirac delta. No. This is a Dirac delta.
The integral over it is 1.
It's a functional. So we will, okay? We will go back to this. It's kind of confusing. Thinking about delta function is always confusing when we will talk about correlation function of this lambda, then we'll go back to this to understanding delta. I'll say it, okay? Delta function, so this is an event, okay? So this would be t. I'm plotting delta now. So this would be delta of t minus ti. This is t. And this, the width of this is delta t, and the height is 1 over delta t. And we're taking the delta of t minus ti is equal to the limit of delta t going to 0 of this. Okay? So that's one way of thinking about the point process. There's another way which is complementary, and rather than looking at the timing of events, would be to look at the inter-event interval. So in neuroscience, we often talk about the inter-spike interval. So we can talk about the inter-event interval. Tk would be equal to the timing of event k plus 1 minus the timing of event tk. So that's another way. That's another way of considering point processes.
Do you consider that the events are with no difference?
Yeah, these are events. We're interested in the timing of events. Yes, events are instantaneous. Yeah, no, we're interested in events that are defined by one time. Yes. Sorry. I want to clarify. An event can have a width, or an event can have consequences that have a temporal aspect. Okay, let's say that these events are phone calls. So if you answer the phone, there will be it will take some time before you hang it up. Okay, but if we're interested in the timing of the phone call, then we're just interested in the timing in which you picked up the phone.
So in spike, what would you define spike? Spike has a profile. So what would you define the moment of peak, the beginning?
So I'll repeat the question because I like it. So how defining the time of a spike? So as a good Jew, I will answer with a question. How do you define a spike?
Active change in the memory potential.
How stereotype is stereotype?
What stereotype?
Quite.
Going above some threshold.
But it could be shaped.
Threshold is enough for our.
There is also a distribution to that.
So another way of asking this question is, if we take two, let's say that all spikes would have been exactly the same. Exactly. Not approximately, exactly. Then it would not have been a problem to define a spike, right? You could take the peak, you could take the time, the first crossing of minus 20 millivolts, whatever you choose. And if you change the definition, basically the whole sequence of events in the brain would change by, I don't know, 10 milliseconds, 100 microseconds or something like that. So in that case, it's not a problem to define the time of the event. So your problem of defining the timing of a spike, in fact, results from the fact that you don't know how to define a spike. That a spike, not all spikes were made alike. So the problem is actually is deeper than the problem of defining the timing of the event. The problem is defining what is a spike. So we are talking about, in our modeling, we always make approximations. So we think about a spike as a stereotypic event. This is an approximation of reality. Not all spikes are identical. Anyone who has ever done electrophysiology knows that not all spikes are identical. And this is not just due to measurement noise. If you look at bursts of spikes, you see that often the magnitude of the spike goes down or go up. It's more complicated. Life is complicated. You should maybe all move to do something else, something simpler. I don't know, math maybe. But in reality, reality is complicated. So this is an approximation. So thinking about using point processes, this is an approximation. You think about events that are well defined in time, have an exact beginning, let's say. And now I can answer your question, which I don't remember. Maybe you did not ask.
What is decay?
Decay is the difference between event k plus 1 and event k. So it's an inter-event interval. I'm sorry?
Between the timing?
Yes, between the timing of these two events.
And what does this give us? Why is it?
Well, it's an alternative way of quantifying the problem. I'll show you later. Maybe I don't know if it gives us anything, but it's another way of thinking about point processes. Rather than thinking about the timing of event, thinking about the inter-event interval. Yes?
But unlike the previous way to look at it, this does depend on the duration of the event or the distribution of the duration of the event. Because we said we can't have two events at the same time. So decay will be affected by the duration of event decay.
No. We cannot have... All our events here happen are instantaneous and have no duration. Maybe we can add duration. We will add duration later. But if we define the timing of an event as tk, I'm just saying that you cannot have two events at tk. Now, another thing that is worthwhile, another worthwhile definition is if these tks are IID distributed, such that the average of t is between 0 and infinity, then the sequence of times is called the renewal process. Okay? Independently and identically distributed. So basically the idea is that you draw T1, T2, T3, capital T, T5 from the same distribution without...
Is it like your whole time range, everything is stochastic?
You draw them from the same distribution. This distribution can be very sharp and then it will be pretty deterministic. But the idea is that...
I meant stationary.
I'm sorry?
I meant stationary.
Yes.
Yeah. But can you still complete that sentence?
Which sentence?
That you still draw them from the same distribution, and
I'll have to rewind the recording to see what I said. But what I meant that this event can also be considered, maybe this is what I meant. My memory span is about 10 seconds. So this is also can be considered as a renewal process. This is very periodic. Doesn't look stochastic at all, and the idea is that the distribution of tk is drawn from this very sharp distribution around this interval.
it's just like really weird to me because like in biology for sure it's not independent. Like
Saying in biology is a bit it's a generalization.
well, like if there was a spike, then immediately after the spike for sure this can be, you know.
If you think about this as spikes, yes. But still, maybe you don't care about. Let's talk about the cortex. Well, we'll talk later about the cortex. But in the cortex, the firing rate of pyramidal neurons is around maybe a few. Sorry? Low meaning? Meaning? 2. Maybe 2 hertz. That would be not unreasonable. In the past, people were debating the rates because the rates that you see in intracellular recordings are different from the rates that you see in extracellular recordings. Can you imagine why?
Intracellular can record something that's from surrounding noise.
So I didn't understand your point.
Maybe you have more noise extracellular.
So why should you get different rates?
Would be lower in intracellular.
I'm sorry? You have to speak up because I'm deaf.
That maybe it will be lower in intracellular, because if you're extracellular, you might also, by mistake, be recording other action potentials from other cells.
So
Maybe, I don't know.
okay, so there are two. That's a possibility, but don't say to an electrophysiologist because they think that the recordings are fantastic, and in some cases they are right. So this is not the reason. So there could be two yes.
Isn't it possible that the membrane can be kind of a low-pass filter and not all spikes will be able to reach your...
No, there's a very high correspondence between what you see extracellularly and what you see intracellularly regarding spikes.
Maybe you're taking the resistance?
So there are two interpretations. One is when you put an electrode into a cell, you're doing many, many bad things to the cell. So D2. So this is an extracellular recording, and whenever there is a spike here, the spike propagates along the dendrite, and there's there's current flowing outside and inside the cell, and this is what we record. This is extracellular recording. Intracellular recording, you take a pipette, you make a small hole in the cell, and so one thing that you do is you make a small hole to the cell. It's not very healthy. So one reason why one could see a change in the firing rate is that by doing it, you damage the cell. One thing that you certainly do is you change the intracellular concentration. So the intracellular concentration is replaced by the intracellular but whatever you put in this pipette. So that's one reason. But I think that another reason, which is what most people believe, is that this is a selection bias. So how do you do an extracellular recording? Well, if you don't see anything, then you don't see anything. You don't know that there's a cell there. If a cell is quiescent, you don't know. But if in intracellular recordings, well, you know that you're inside a cell. So even if the cell doesn't fire at a high rate, you still know that you see a cell. So that would be a selection bias. But putting these things aside, the rate is few hertz. If we think about the pyramidal neurons, maybe 1 hertz. So this is a rate of events. Now you were talking about the refractory period, the fact that two action potentials cannot coincide. What's the time scale, the refractory time scale? I'm sorry? Well, about a millisecond and more. Maybe 1, maybe 2 milliseconds. So if you think about a neuron that fires at 1 hertz, who cares about these 2 milliseconds? Well, maybe the brain cares, I don't know. I don't. Yes?
Well, also assuming here that the rate does not depend on the time, which is weird because you do different stuff at different times, you do different tasks, and you kind of assume that the firing rate doesn't change according to that.
No. That's not what I said. I just said if we take this, then it's called the renewal process. That's it. That's all I said.
You're going to assume it too.
No, I'm just saying that's it. You don't like this approximation. Fine. That's fine. That's good. This is what a renewal process. That's the name of the process. It's called the renewal process. If you think that it's a poor approximation, fine. Yes.
Doesn't this condition of on the average cover all of this? What other
Well, you could. There are some distributions in which the average diverges. Power law distributions.
But here the average diverges. No?
No, I'm considering distributions that have a mean that does not diverge. There are distributions that don't have this property.
So this is an example of regular.
That's the name of a renewal process. That's all. We will talk about the brain soon. Don't worry. We're just building. I'm just putting forward the building blocks for modeling neural activity. And you can, if you don't like the assumptions, if you don't like it, then there's nothing you can do about it, right? Because I'm the teacher. Okay. I enjoy power. So I hate noise. Okay. One process. One point process that is particularly useful is called Poisson process. Poisson process. So the idea is the following. So we divide time into bins of size dt. And we assume that the probability of an event in the bin is lambda t is lambda times dt. And particularly, we're interested in homogeneous Poisson process in which the probability, the rate, is a constant lambda t is equal to lambda. So this is a Poisson process, and this homogeneous Poisson process is just defined here.
Such that within the bin?
I'm sorry?
Such that within the bin the probability is always the same?
The probability of an event in a bin is lambda t dt. And we take the dt to 0, and in a homogeneous Poisson process, lambda is constant. This probability is constant. So
And then it must be, can be whatever.
I'm sorry? We'll take the delta t to 0. We'll take the limit of delta t to 0. Yeah. So the first thing to do is, what is the distribution of the number of events in an interval so we consider a homogeneous Poisson process, and we want to compute the distribution of the number of events in a particular interval. So how are we going to do it? So we're going to, so let's say that this is t. So how many bins do we have in an interval t? How many intervals? So the number of intervals is simply t over dt. What is the probability of event in an interval? This would be simply lambda delta t, right? So the probability of k events would be equal to what?
The power of k.
So, sorry?
K. Not lambda delta t.
Let's call this p, just to. So this would be the limit of delta t goes to 0.
I didn't see this limit.
You didn't see the limit coming.
Yeah, so I'm not sure, but I still think that it might be like something like lambda delta t.
Let's call it p again.
P
So p
to the power of k.
k.
That's what I thought.
Well, clearly you're wrong. Why?
Because that's the first time I think about it.
No. You could be lucky.
Yeah,
right?
I'm not lucky. Polish.
The thing is that this, the limit delta t goes to 0. This will go to 0.
Right.
So we have n intervals. So what's the probability that k of them, there will be an event in k of them, and there will not be an event in all others?
N should k,
pk,
p.
1 minus p to the power of k. So this is a n minus k, I'm sorry. So this is a probability of an event happening in the bins. This is a probability of an event not happening in all other bins, times all the possible permutations. So we can have all events in the first k bins. We can have all events in the last k bins. And as you said, the number of permutations would be simply n over k.
Can you repeat what you told me before?
This is a probability that you graduated. You got your PhD with distinction. You published 2 Nature papers while being a PhD, and now you work in answering phone calls and you have to. And the question is, how many phone calls will you get? This is not meant for. I apologize. This was inappropriate. The question is, how many? If you have a rate of, let's go back to neuroscience. Okay, I will stop offending students and go back to neuroscience. So you have some probability of event. Let's say it's a Poisson process, and I want to know within 2 seconds how many spikes am I going to get? That would be the question. How many? So what's the probability that I will get k spikes in an interval t? But the important thing, and I'd like to emphasize, this goes way beyond spikes, what I'm doing here. This is true for biology in general, but for life in general, because this is like the most common thing in life, this Poisson process. You'll see it everywhere. Everywhere in neuroscience, in cognitive sciences, in economics, everywhere. In chemistry, this is like the most important thing that you'll ever learn. Yes?
But why do you think that all events are in the same way? Maybe that's something I'm missing. Why the K events are in the same way?
No. This would be to get K events overall, over the interval T.
So why are you multiplying by the probability of having no other events and other things?
Because I'm asking what's the probability of getting K events in these bins, but not more than K events.
But it's like you're limiting it to one bin. Like
No. So in K of the bins, I will get the event. In N minus K of the bins, I will not get the event.
you can get only one event in one bin?
That in the limit of delta T going to 0. Because we can't have two events at exactly the same time. Yes?
What makes you assume that something is Poisson process?
Nothing. I'm saying if it is a...
Yeah, but you said many things are Poisson process.
Well, I will show you later.
Okay.
Faith. I will show you later events. I will show you later. Believe me. I will show you 3 examples, and only one of them is coming from neuroscience.
The phone call thing is Poisson process.
Kind of. Again, it's an approximation. That's like if you... In the 90s, when I was a student, and this was before the time of internet, and before the time of computers, and before the time of cars, this was an example that people would bring for a Poisson process. Somebody that would answer phone calls that come all the time, like this would be this would be the example that people would bring for a Poisson process. It's not exactly true because at 4 a.m. fewer people call than during the day, but still, if you think about an interval, it's a good approximation. So that's why I came up with this horrible example. I apologize again. It's yeah, I will ask Kasher will before Kasher. I will not teach this course next year, I'm sure. Okay.
One little question. N is the number of intervals?
Yes, N is the number of intervals. Sorry. More questions? Yes.
Did we assume that lambda is independent of T?
Yes, for homogeneous. It's called homogeneous Poisson process. Lambda is independent of T. So all we need to do is compute this, which is straightforward. So how are we going to do it? Well, this would be so here we'll have lambda T over N limit of N going to infinity of lambda T over N to the power of K, 1 minus lambda T to the power over N to the power of N minus K times N factorial N minus K factorial K factorial. Right? What's the next step? Yeah. It's not a bad idea in the sense that whenever you have factorial, it's a good idea, but I'm not taking the limit, well, at least not of K. So we will write it like, so this would be the limit of N going to infinity of lambda T to the power of K, 1 minus lambda T over N to the power of n times 1 over k factorial n factorial over n minus k factorial times n to the power of k. Right?
Not exactly, right? You did
It's
say
exactly. It's exactly. I didn't do anything wrong. Not this time.
no, that's fine. Whatever you do is fine. It's not like you didn't approximate.
No approximation. Nothing. I just moved things from one side to the other. Nothing.
You understand? You need n minus k in the exponent.
Ah, no. This.
Yeah, that's why that is
Thank you.
Yeah. Times
Okay, that's
1 minus lambda t. Sorry.
much better now.
Okay, I'll spend the rest of my class here. Yes, sorry. But now it's okay, right? Okay, so let's see what we have. So we have lambda t to the power of k. That's fine. 1 minus lambda t over n to the power of n in the limit. This would be exponent, e to the minus lambda t. 1 over k factorial will be, well, 1 over k factorial. What about this term?
Can you repeat what you said before?
So this is equal to lambda t to the power of k. That's the first term. What about the second term in the limit of n going to infinity? It's an e to the minus lambda t. That's the second term. Third term remains 1 over k factorial. What can we say about this term? So this would be n times n minus 1 times n minus 2, n minus 3, until n minus k plus 1. So we have k terms. Now here in the denominator we have n to the power of k. So let me write it here. So we can write the n factorial over n minus k factorial n to the power of k. This would be equal to n over n times n minus 1 over n times n minus 2 over n times n minus k plus 1 over n. And we take the limit of n goes to infinity, so this will be equal to 1 in the limit. Okay? And we have the second limit of n going to infinity of 1 minus lambda t over n to the power of k, which will be equal to 1, because this will go to 0.
What goes to 0?
Well, because this term goes to 0.
So why doesn't the exponent term go to 0?
Because we have n here and here.
Why does it matter?
Because we're taking the limit of n go to infinity. So this will go to 0, but to the power will. So the question which will dominate, this one or this one? This n or this n? Here you only have n here.
The lambda t over n goes to 0 anyway.
Yes, but you take it to the power of n. You do it n times.
So we're taking like it's 0.
So does anyone know what this is called? Poisson distribution. So that's how the two are related: Poisson process and Poisson distribution. So, okay, so that's a relationship between the Poisson process and the Poisson distribution. And here I'm going to give you an important tip for simulations that will help you, hopefully, throughout your lives. Even the younger ones that will expected to have a long life. So, how are we going to simulate the Poisson process? How would you simulate a Poisson process? Naively, so let's say I'm telling you, your homework assignment is please simulate a Poisson process. So a Poisson process, well, the probability of an event in the bin is lambda delta t. So we take time, we divide it into n bins. Well, we take as many bins as possible. We toss a coin in each and every bin to see what would be the outcome, and then we fill the bin with pluses and zeros. That would be one way of simulating a Poisson process. Now, if you have a stronger computer, you'll take a larger n. If you have an even stronger computer, you'll take an even larger n. That would be naively the way to simulate a Poisson process. But there's a better way of doing it. Well, a better way, what's the price? The price that you need to do this drawing stochastic numbers n times, and in the limit of n going to infinity, that's kind of expensive. And the answer that you will get is a very large vector that mostly contains zeros. So, any suggestions based on what we have just said? So that will be the third possibility. You can draw the time between events, but you need to know what's the distribution. You will know, but not at this point in time. In half an hour, you will know, but that's the third possibility. So one possibility is to compute the distribution of these t's, and then draw these t's from a distribution. That's a third possibility. First possibility is the non-efficient one of dividing t into bins and drawing event in these bins. But the most efficient way of doing it is to say something like the following. Well, I know the rate, I know the duration, so I know what the distribution of the total number of events. The distribution of total number of events is this one. It's a Poisson distribution. So first I'm going to draw the total number of events in this process. That's the first step. Now I need to distribute them along this line. How am I going to distribute them along this line? Uniform. They will be uniformly distributed. So rather than dividing this into n events and every one of them drawing an event with some probability, all you need to do is first draw the total number of events, uniformly distribute them along this line, and then you'll get, this will be a simulation of a Poisson process. There will be one realization of a Poisson process. It's a very useful piece of information. One day you will thank me. Yes?
K is the number of events.
Yes.
Right? So this expression is the probability to have K events.
Right.
So why did you refer to it as the number of events?
The number of events is K, and we computed the probability of having K events. Not sure that I follow.
Okay. If I multiply it by 100, so I get the number of events. This. Because it's the probability for having K.
Well, that's the probability of having K events. K can be 0, 1, 2, 3, 4, 5, 6, and so on.
Okay.
You can have an infinite number of events, but with a very low probability. Not sure that I understand your question.
Yeah, maybe I should check my question again.
Let's take a break. I will hide somewhere, and then we'll get back. Yes.
For the periods of t, so if you want to draw the probability, so this bar is k, this bar is probability, so you draw something like this, right?
Can you mark again? Sorry.
You want to know in periods of t how many events will it have, right?
How many events are you going to have here?
Yeah. So I can draw something like this. This bar is here. So this is the k event. This is the probability.
Yes.
So and then you draw this function. So I don't know what it looks like, but I think
I know. Yes.
Yeah.
So it looks something like this. But it will be discrete.
Yeah.
So it will go up and then k exponential.
Yeah, that's what you're talking about.
About the number of events. Sure, but I don't know, maybe someone else has already volunteered. Has anyone volunteered to take notes?
Did you take notes for Itmano? I never taken notes yet. I haven't taken notes yet in first class. I haven't taken notes yet. No, I mean the previous class. So Itman, bonus of no.
אני יכול בזמן ניסוי הזה לחלום כמה אירועים אמורים להיות
is the king of nodes.
וגם
so have you not taken notes yet? Yeah, I have not taken notes yet.
עכשיו שאני יודע כמה
Just tell you tomorrow.
כאילו יוניפורם בכלל זה ממש הרבה יותר
Yeah, I told you at the beginning of class. I come an hour late. So it's like only 1 day a week. Okay, there's a few more classes left.
Okay.
I think there's not many people.
Okay.
It's why did you take notes into the phone?
שלוש אופציות. שתיים, there are basically three options. The first one I didn't want to discuss, but it's a valid one, is based on the distribution of inter-event intervals. So if you know, if you draw the interval in the distribution, if you draw the distribution of intervals, you can draw them from this distribution, and then you take the first one. So this will be interval 1, this will be interval 2, this will be interval 3, and this will generate timing of events. Okay, that's one way of doing it. The second way of doing it, which is the most naive, is just to divide t into bins, n bins, and each one with some probability lambda times t drawn event. You take the limit of n goes to infinity. Then, when you have to do any calculation, the accuracy will be 1 over delta. And the third one, which is like the most efficient, is first say, well, I don't know how many events are in the distribution of events. So the first step would be to decide on the number of events that will happen. And this is of course a stochastic process, and so I draw it from this number. So this is what I calculate. So let's say I got 5. So now I'm going to uniformly place these 5 events along the keyboard.
What's clear to me is that anyway, if I want to simulate over some time, then I have to divide it into weeks.
No.
Because I have
You have 5 events. Okay, so now using run MATLAB.
Okay, and then I just
draw
have
numbers between 0 and 1, and then multiply them by t, and just draw 5 random numbers between 0 and 1.
So I don't have a vector of 0s and 1s.
Just have the 5 events.
Clear to me now. Great.
Yes.
Alex,
כן, הספקתי את הכזה, ונשחרר מהרכבת,
כן.
כאילו, אם נגיד ההסתברות לקבל כאב היא 100, אז אני אחלק כאיבנט באמת,
נניח שאתה... לא, אין דבר כזה. סיכוי לקבל... הוא אף פעם לא יהיה אחד.
אז אם הסיכוי הוא לא אחד, אז אני לא אקבל בדיוק כאיבנט, נכון? יהיה לי איזשהו מספר ליד כאיבנט של אירועים, נכון?
לא. בוא נתחיל בניסוי. נניח שאתה ניסוי של תהליך פרוסס, חוזר עליו מיליון פעם. עכשיו אתה בוחר ריאליזציה אחת של ניסוי. בריאליזציה הזאת, K יהיה שווה 5, או 6, או 12, או 3, יהיה מספר אחד בריאליזציה הזאת. עכשיו תעשה את הריאליזציה הזאת כמה פעמים. תסתכל על כל הריאליזציות, תראה לך איזה התפלגות על K. זאת תהיה ההתפלגות על K. זאת תהיה ההתפלגות על K. ואתה מתעניין בריאליזציה אחת, תיקח דוגמה אחת. אם אתה מתעניין בכל הריאליזציות, תיקח את כל הדוגמאות.
אז אם נגיד כל התהליך הזה הוא ארוך באורך של T, אז יהיה לי בדיוק זה אירועים. כאילו אתה אומר לי התפלגות...
אני לא יודע כמה אירועים יהיו לך. לפעמים יהיו לך 3 אירועים, לפעמים יהיו לך 17 אירועים.
כן, אבל זה תלוי באורך של האינטרוול.
כן, גם כמובן תלוי באורך של האינטרוול.
והלמדה זה פשוט מובנה בתהליך. אז אם אני לוקח אינטרוול כזה, אז יהיה לי ככה אירועים.
כן. זאת אומרת, סביר, לא? אם יש לך אינטרוול יותר ארוך, יש לך יותר אירועים.
אני חושב שרק כל הזמן בין השיעורים, סליחה...
לא. נהנה להשפיל את עצמי בשיעור ושלא בשיעור. שנייה.
השאלה היא לא כמה אירועים יהיה, ככה סיכוי עבור מספר שבוע. כלומר, האם ככל שהאינטרוול מתרחב, הסיכוי עבור שבוע.
כן.
שאלה ממש כאן נוגע, ממש בקטע של השיעור. אז הגדרנו את סטנדרטים הגדרנו את סטנדרטים וקוראים, אתה מבין איך התחום הזה הוא רואה, ומה זה בעצם, על מה אנחנו רואים ומה פה זה TI זה הזמנים. TI זה הזמנים של איבנטים. אני מדבר על כל הזמנים שהגיעו איבנטים בהם. אם נסתכל בגלל תחום, אז יש פה משהו דלטה בזמן TI. ממש כמו שיש תחום, למה אני יכול להשתרק? אם נסתכל לראות את הסכימה מבחינת משהו.
בדיוק.
זה לא לפחות, זה לא לפחות איפשהו. כן.
הוא דיבר על ריאליזציה,
גם ממוצע.
כן, תמיד הגדרה של...
זה ממוצע
אתה יכול לחשוב על זה כעל... אני מגדיר את למדתי בצורה הזאת. זה הגדרה.
מה שקורה פה
TI זה הריאליזציה, זה של הריאליזציה.
אוקיי.
כן, אם יש תפקיד, סיכוי לקיים.
אז אם יש בן ב-TI, אז יכול להיות תפקיד פחות TI.
בטח זה איזשהו, יש לו איזה פיק.
השאלה שנייה שיש לי לך, בנוגע לסמל ספרי פרוטון, אתה מתעלם מזה שאולי בכל בין כזה יש אימות לפרוטון, ואם אני עושה אינפורמט, אני מתעלם שאימות. אני שוב חושב לתהליך בעצם
מדברים על תהליך פרוטון הומוגני.
נכון, הומוגני. בכל דלת כזה, אני באמת אקבל משהו שהוא בתוחלת למדה, אבל תכנו מצבים שבהם מקבל יותר פחות, כי התפלגות, כי עדיין משתנים טיפ פה למדה.
אתה מדבר על ממוצע ריאליזציות. תעשה את התהליך הזה אין סוף פעמים.
נכון, אז ככה, ואז אני מקבל נכון. זה לא הלכתי למועדות מיני. הכל היה מתשקיע.
Okay. I'd like to continue. I'd like to continue humiliating myself. So we spoke about the homogeneous Poisson process, and we concluded that the number of events, distribution of number of events, is a Poisson distribution. And now you understand why Poisson got the credit for both of them. So the next question is, what would be, thinking about this thinking about the renewal process, what would be the distribution of inter-event intervals? So what would be what is the distribution of inter-event interval?
You mean the length?
PK.
So by the distribution, you mean what will be the length?
Yeah, distribution of length. So what's the probability that T will be between two intervals, between the interval of T and T plus delta T? Basically, that's a question that interests us. Do you all understand what I'm doing? Do I understand? No?
Previously, we did probability according to K events, and now you...
I'm looking at one of the events. I just wanted, let's remove the index, just because we use T for the entire duration, so it's kind of, it's not this T. Okay?
So why did you erase K?
Because he told me to.
But then it looks like that T.
Okay. So I'll bring it back. Sorry. We can vote on it if you like, but let's do it after class. Okay, so that's the question. What would be the distribution?
Depends on somehow on what we did last
Last?
lesson. The Poisson distribution.
Why? What's the thing that is deleted here, you mean? Well, basically, what's the meaning of the fact that Tk will be equal to T? It implies that there will be no event for T prime that is smaller than T. So there will be no event until this point in time, times the probability that there will be an event at interval T and T plus delta T. Right?
And afterwards?
We don't care about afterwards.
T is the time between two events, right?
Yeah, I'm looking at two events. So starting from this event, this is being time 0, I need that there will be nothing here and something here. An event here. I don't care about what
What is that one?
What is the first line represent? No. The drawing, הציור שציירת על הקווים, כן.
So there was an event this time. There was nothing until this.
Which time point?
So I'm interested in intervals. So I'm looking at starting from one event. I'm looking at the interval from this event to the next one. Did I answer your question?
Can you label
because I still didn't go.
With T and T plus delta T?
Okay, this would be Tk, and this would be Tk plus 1. Yeah.
I'm not sure what it means that Tk is a member of this interval. Shouldn't it be for this Tk is equal to something?
That's a good question. First, it doesn't matter, but just for consistency, I'll use this interval. The issue is that you will never get an exact interval. This is a continuous distribution. So what's the probability that you'll find a person with whose height is exactly 175? Probability is 0. You never see. Okay? So the probability that it will be at exact interval is 0. We're interested in the probability of being between t and t plus delta t. Yes?
Why do we demand that there are no events prior to TK?
Here, for example?
Prior, for t.
Yeah, you don't have
smaller
the
than
figure.
TK.
This is tk. The interval between tk plus 1 and tk.
Yeah, but why do we demand that there are no events for
Here?
t tag? No, the first probability.
No events for.
Yeah.
Because I want this to be empty.
Okay, so
Otherwise, this one will be the next one.
That should be between tk plus 1 and tk.
Yeah. I see. No event for tk smaller than tk. Yeah, the notation was wrong. Yes?
Delta t of this is approximately going to 0?
Yes. We will take it eventually to 0, but I asked what's the distribution. This is how I do it. I look at the distribution, then I will take delta t to 0.
Why is it not just 0?
Again, we're talking about distributions of continuous variables. Okay? What's the probability that you'll find someone with a height 175? The probability is 0. It doesn't mean that you can't look at probabilities of height of people.
No, but if you are multiplying in probability of event in a very, very, very small interval, it's going to be 0.
It is going to be 0. All continuous distributions are always equal to 0. And the probability of finding someone with an exact height. So the probability of getting an exact value will be 0. What we care about is the distribution. Allow me to continue, and then we'll go back to this question. Okay? Okay, what's the probability of no event? So the probability of no event is 1 minus lambda delta t to the power of t over delta t. Right? Probability that there is no event in the first bin, the second bin, the third bin, the fourth bin, and there are t over delta t such bins in which there will be no events.
Can't you use the Poisson distribution for this?
I can. It'll be the same. What's the probability of an event in the interval t to t plus delta t? This is probability is just lambda delta t.
I'm sorry to stop you, but it seems like you should have probability for an event and then a probability for another event. I don't understand how you have like no event and one event, because we're talking about an interval between two events, right?
I'm starting the count from the last event. So there was an event. So I'm asking.
This is not no event since the last event. So.
Because we're talking about an interval. So we start counting from the last interval and then moving to the next one. So taking the limit, this will just be equal to e to the minus lambda t times lambda delta t. So if you want the probability distribution, just throw away the delta t. Does that answer your question? Guy?
Answers the question. I'm not sure why, but it does, but I'm not sure why you can just throw the delta t and get the distribution.
Again, let's talk about the normal distribution.
Okay.
So this is a normal distribution. Zero mean, 1 standard deviation. What's the probability of getting this particular value in a normal distribution? 0. What's the probability of getting this value in a normal distribution? Still 0.
Yeah.
even less than 0. But still, that's not a question. That's not an interesting question. I ask stupid questions, I get stupid answers. The question that I should ask is, what's the probability of having a value between these two intervals?
I understand that you want the distribution. I just don't understand why if you remove the delta t, that's what you get.
Well, that's the probability of getting a value between t and t plus delta t.
Okay.
So what you will get is that this distribution looks like this. It will be an exponential distribution, and this would be the, if you want to know what's the probability of getting a value.
Got it.
Okay?
Thanks.
I thought that you did similar things somewhere, sometime. Maybe I was wrong. Okay, so the distribution of inter-event interval is exponential, right? So this would be a signature of these processes, an exponential distribution of inter-event interval. It's not a proof, but it will be a signature. Second, technical issues. Yes. A Poisson process will result in exponential distribution of events. So if you measure inter-event interval and you see an exponential distribution, and you find exponential distribution, then you may hypothesize that a Poisson process is a good approximation. So I'll show you several examples. This is a distribution of inter-event interval, something that I did some years ago. It kind of looks exponential, except for these two outliers, which I don't exactly understand. Anyone wants to guess? What generated this distribution? Well, you cannot guess. That's a waste of time. So I was doing a study on decision-making of obstetricians. Okay? That was the topic of research. The paper came out 3 months ago. But just for the fun of it, what I looked at is the distribution of inter-delivery interval in a particular hospital.
The baby?
Yeah. Okay? Yeah. The timing of arrival of the inter-event interval. And to a good approximation, it's exponential. Now, this is not surprising at all. Why is it not surprising? Because the events are independent. If I go to labor, maybe it's not a good example.
But if there's baby,
still I will not go to labor.
no.
But for the sake of argument, if I go to labor, it does not mean that it has nothing to do with you going to labor, except for the case of a baby boom. But again, I mean, sure, if a baby boom would have been an important factor in the analysis, then you would have expected to see a deviation from exponential distribution. So to a good approximation, assuming no baby booms and similar things, the distribution is approximately exponential because the events are approximately a Poisson process. It's not exact. For example, fewer women give birth on Saturday. Yes. Fewer women give birth.
It's only because
psychological effect. So when you
Well, first it's effect.
you can hold it, you can let go, and stop.
First it is effect.
In Israel or in general?
In one hospital in Israel that I studied, okay, in Jerusalem, Hadassah Har HaTzofim. I think it's also true for Hadassah and Karen. Now there could be different interpretations. One is that there are many religious women, and they would do everything that they can not to drive, not to Lechalel Shabbat, not to go on Saturday. Or maybe they will not go to Hadassah, I don't know. But this is like a small effect. That's a small effect. It's not a strong effect. Actually, if you look at the literature, even in civilized countries, you see a difference along the days of the week. Like not Israel. Yeah. You see fluctuations along the week. There are fluctuations along the day. If I remember correctly, fewer women give birth between midnight and 6 a.m. Something which you can still. I mean,
how many years did you?
This is not a lot of data, but we were looking. This is known. I mean, these things are known. It's not again; these are small effects. But so, if you really want to find deviations from exponential distribution of interval or deviations from a Poisson process, you will find. But to a first good approximation, these events are Poisson, and as a result, the distribution of events is exponential. Put differently, you as researchers studying something, you see an exponential distribution, first thing that you need to think about, you say, maybe a Poisson process is a good approximation.
How did you define the interval in this case? The interval?
Well, there's a recording of when the woman gave birth. Okay, if you look at the details, you find, for example, that more women.
No, but how did you decide? Like, choose randomly 2 points?
No, look at the entire sequence of events. Each one has its own date, time, hour, and minute, and you look at the difference in this vector. That's all. And look at the distribution. Yes?
Can I just ask how it's related to neuroscience?
No, this is not related. Well, why did the question that you can ask can have two. Can be asked on two levels. How come that I work here in this department and I do this? Well, when you have tenure, you do whatever you want just for the fun of it. That would be one answer. But that's the reason. Another question, which is perhaps more relevant. Another question that is perhaps more relevant is why do I waste your time here to tell you about it? This is a much more relevant question, and the answer is to make a point. And the point is that exponential distributions of events, and we will soon go back to neuroscience, is something that is widespread and is a signature of a Poisson process. Yes?
Yes, this is convincing. It does look like this is the PDF for exponential, but I'm sure I can fit an exponential to it, but I might as well fit another function. Is there like a threshold of goodness or fitness that you can, or just a qualitative?
Okay, here. This is an important discussion. I don't know if I want to waste your time on it, but the point is the following. So if you will do a significance test, you will find that this is not an exponential distribution. This is not an exponential distribution for at least 2 reasons. One reason is that you have these 2 events. These are extremely unlikely. My interpretation, there was a problem in the coding of the event. Okay? But looking at the data, if you take a statistical test, immediately you can rule out the exponential distribution and say, okay, this is not a Poisson process. Second, I already told you that there are weird things. Fewer women give birth on Saturday. There are differences in time along the day. If you look more carefully, there are differences along the year. So it's not distributed uniformly during the year. I can't remember when you see more deliveries. I had a hypothesis that it's related to vacation and teachers, but I never tested it, and so I don't know. So if you want a statistical test, you will find, if you have enough data, you will be able to significantly rule out a Poisson process. But this is not what we are doing. We're just approximating. Everything that we do in biology is we make approximations. So ruling out a hypothesis is easy, but it's not very meaningful. It is a very good approximation. And it tells us something about the mechanisms. Okay, another example. At some point in my life, I was wasting the taxpayers' money in studying basketball, behavior in basketball. So you all know how to play basketball. Basically, you need to put the ball in the basket, right? That's why it's called basketball. And there are at least two ways of doing it. You can do it from far away and get 3 points, and you can do it from nearby and get 2 points. 3 is better than 2, but more difficult.
Are these the actual rules?
I'll ask Itamar for an extra hour on basketball. Okay, so you can look at the sequence of events. And the events here are defined as attempts. So you hold the ball and you make a decision to make an attempt. Ah, Itamar, we were just talking about you. We want you as they want an extra hour on basketball. But play, explain the rules.
I don't believe that there's no such thing as a hot hand.
Okay, we will not talk about hot hands here. But basically, you have a sequence of events. You have a sequence of events. So this becomes a point process. And we can quantify the distribution of inter-event interval. So for example, the interval between 3-point attempts or the intervals between 2-point attempts. So this is just an example, Kobe Bryant, when he was still playing. So what you see here is this is a distribution of inter-3-point intervals. It's pretty exponential. Oh, you'll be surprised how much information there is out there. Yeah. It's a lot of fun. 2 points, inter-event interval in 2-point shorts. Again, this is approximately exponential. Now, you have to remember, a game has a duration. So you cannot have an interval that is longer than the game. So obviously you can rule out the exponential distribution. You cannot make 2 attempts at exactly the same time or with an interval of 1 millisecond. And indeed you see this bar, which is shorter than expected by an exponential distribution. So this is kind of a refractory period. It's kind of a refractory period. Now, that was not the point of this paper, and we will not talk about the point of the paper. But the point is that this is a good, an exponential distribution is not a bad approximation of the inter-event interval, or a Poisson process is not a bad approximation for the timing of events. Now the question is why? Well, there are two whys. One, why am I wasting your time on basketball? I think there is a reason to it. But the second why is why a Poisson process is a good approximation to a behavior of basketball players. Yes?
You wouldn't want the rival to know that you're going to throw the 3 points, so you have to do timing.
This is a possibility. I don't think that this is a reason. So you say that this comes from strategic reasoning, but the thing is that you know it's kind of obvious that you're holding the ball. There's nothing to hide here, and that you're going to do something with it. So in that sense, in other fields, people have made this point. In tennis, for example, people have argued that there's a study on Nash equilibrium in Wimbledon matches, and there's a study, I think, in soccer about fouls in soccer, but I don't think that this is the explanation here. Yes.
The chance, the probability of events to happen in the same time interval is not changing so much during the game.
So I think that the answer is something like that. So in basketball, to those that know the rules, basically what's happening is that every time that you score, the ball goes to the other team. That's one thing to know. And the second thing, that players constantly pass the ball from one another. So if you look at the numbers here, this is for one of the players that scored, that spend a lot of time with the ball. The intervals are on the order of inter-event interval are on the orders of tens, or I don't know, maybe 10 minutes or several minutes. Now the ball passes from one player to the other every several seconds, from one team to the other every several tens of seconds. So the game, if in a more we can think about it as a mixing process, as a mixing stochastic process. So there are many events taking place in the game that are stochastic or partially stochastic between every attempt. And as a result, the attempts become, on these time scales, they become approximately independent.
Also the 2 and the 3, if you took only attempts, I think you'll get...
It's more complicated, and of course this is just an approximation, and one can write a paper about it, but this is not the topic here. But the idea is that if you have mixing, if you have the events, the timing of events is the inter-event interval is much longer than the mixing time of the system, then you expect to get, this is another mechanism by which you expect to get an inter-event interval, which is exponential distribution, and put differently, the timing of events would be approximately Poisson. Questions? Okay, just neuroscience, back to neuroscience. So, one paradigm, one experimental paradigm that is kind of going back to neuroscience, you can sue the university for wasting your time on basketball and deliveries. But so now we go back to neuroscience, and one very standard and very popular experimental paradigm is known as the moving dots paradigm. Basically, what you have dots moving on the screen, and the simplest cases are correlated. For example, all are moving up or all are moving down, and the monkey is instructed to say moved up or moved down. That would be one paradigm. Another would be that, and this is easy, you can have 50 moving up and the rest moving randomly. That's more difficult. Or you can have, the fewer moving up or the fewer moving coherently, the more difficult the task is. And that's a standard task to study perceptual decision making in monkeys. That's very standard. The most difficult, of course, would be the case where they all move randomly with no correlation, and then there's no right answer. And I will show you some results from such experiments. And so this is experiment. This is and these are experiments done by Shadlin and Newsome over 20 years ago. And I can't remember whether this was, maybe you know, whether this was intentionally or by chance. They used the same seed. So they presented the monkey again and again and again, exactly the same stimulus, with exactly the same variability, exactly the same motion. And what you see here are many repetitions, and recording from a neuron in a brain area known as MT, brain region that is in which neurons are selective to motion. And well, this is the average. So you see this random or irregular timing of spikes. So what you see here is the average over many repetitions, and you see that there is some modulation. And this is not surprising because, well, these neurons are sensitive to motion, and at different points in time, the points are moving slightly different in a different way. So this is the deterministic part of the activity of these neurons. But if we look at just a small part, let's say in this region, this is how the spike trend looks like. So basically the rate is approximately constant, and the timing looks rather random. And if we look at the inter-spike interval, if we look at the inter-spike interval of these neurons, it is approximately exponentially distributed. You see that there's no beam here. It's 0. But other than that, it's approximately it's well approximated by an exponential distribution. So why do you think that there are no spikes here?
It's time for it to recharge.
So one interpretation would be that the reason that there are no spikes here are physiological. The reason that the neurons have a refractory period and they cannot fire two spikes in a row, for example. That would be an interpretation.
Maybe we can see it.
Well, that's one interpretation.
Well, like the memory effect.
So this is something, it's heresy, so something about the physiology. That's one interpretation. That would be the common interpretation, perhaps also the true interpretation, but there's another one.
When you measure, you can image.
Okay, so when you measure, when you do electrophysiology, you asked me previously when we talked about extracellular recording, and we talked about the fear of recording from two neurons and thinking that they are one. So one way of avoiding it is you look at the distribution of inter-event interval, and if you see that there are many cases in which the inter-event interval is too close, then you say, okay, this is not a single unit, I'm not going to use it in this analysis which relies on single unit. But this is kind of circular, right? Because basically you will not see these events because you rule them out. There will be a selection bias against neurons that show events here. But this is just a side note. Okay, another thing that one can do, we didn't talk about it when I showed you the Poisson distribution. When we computed the Poisson distribution, one can look at the variance as a function of the mean in the Poisson distribution. It turns out that in the Poisson distribution, the variance is equal to the mean, and you can look at the variance as a function of the mean count looking at different intervals, and it's approximately linear, not exactly, of course. So the variance over the mean is the variance is approximately equal to the mean. The variance in the spike count, as predicted from a Poisson process. Yes.
Are we talking about the variance in the mean
of the number of spikes? Number of spikes. Another thing that let's go back to the whiteboard. So going back to the distribution of inter-event interval, this distribution is approximately exponential, right? So we can compute the average inter-event interval. So what would be the average inter-event interval? So this would be just the integral from 0 to infinity of t times lambda e to the minus lambda t dt.
I'm a bit confused by the notation.
Let's use capital T. Okay. Sorry. I will punish myself later. Okay? So this turns out, if you do the integral, this is just equal to 1 over lambda. And we can look at the variance. How are we going to compute the variance? Well, basically, we'll compute average of t squared and subtract t average squared. And to save time, I will tell you that the answer is 1 over lambda squared. So it turns out that a quantity that is known as a coefficient of variation, CV, which is defined as average delta square root of average delta t squared over average of t, is equal to 1 for a Poisson process. So another signature of a Poisson process is that the CV is equal to 1. So now we can go back to neurons in the cortex and ask ourselves, well, what's the distribution there?
What T is
Average inter-event interval. So it's average inter-event interval. So this is what we discussed, just the different notations. So the average, let's look at this coefficient of variation. So if it's very periodic, then the variance is expected to be very small, and then the coefficient of variation is expected to be very small. For an event that is completely periodic, the CV will be equal to 0. If it's irregular, the CV will be larger than 0. So CV is a standard measure of irregularity of events. So now you can ask me what is a CV for the deliveries, or what's a CV for the basketball, right? Well, you can ask me. I don't know. I haven't done the calculation, so I don't know. But more interesting for us is CVs in different cortical regions. And what you see here, this is a study in which they took many, many neurons in 4 cortical regions and computed the CV for these neurons. Yes?
We showed that the Poisson process got CV1, but it's not implied CV1 is a Poisson process. So
Absolutely. Absolutely. But bear with me, okay? So the claim is that in many cortical regions, the distribution of CV is not too different from 1. Again, it's not, well, you can argue that once you find something that is not exactly 1, you immediately rule out the Poisson. So there are 2 things, right? One is, if you see CV that is not 1, you can say it's statistically significant, not Poisson. But it's approximately Poisson. Poisson can be sometimes a useful approximation. That's one thing. And second, you say, even if it's exactly 1, there can still be structure. Right, that would be one measure, just one measure. There are other measures, for example, looking at correlation between consecutive intervals. This is, I think, called CV2. So there are many measures that people use in order to quantify the irregularity in the firing of the neurons. But one point that emerges from this and other measures is that Poisson firing is a good approximation, or is often a good approximation, to the firing pattern of cortical neurons.
Are there exceptions?
Always exceptions.
I mean, not individual, structure, like more large scale.
Again, if an exception for you is substantial, then to the best of my knowledge, I think that there are people who argue against it in the auditory cortex. Tony Zader has made a point against this Poisson assumption for firing in the auditory cortex, but I think it's a very useful and good approximation. Yes.
So I'm not sure it's a relevant question, but so if everyone fires Poissonally, so where is the information? In the deviation from the Poisson, or?
That's a very good question that I'm not going to answer. Well, I'm not going to answer in detail. I have to say two words. First, some people will say, it looks Poisson, but in fact, the exact timing of event is very important. That would be one thing that people would say. Another is that the overall rate is important. So it's not homogeneous Poisson. So, and actually, we saw examples when we talked about the selectivity. We saw that there's tuning. So the firing rate itself, the rate of event is something that could code information. You had a question.
I'm just seeing that basically all the cells here are irregular.
Regular? No, regular would give you... But irregular in a particular way. There are various ways of... You could be irregular in many different ways. One of these ways is Poisson. There are other ways of being. You can fire a burst and then rest a little bit, another burst. This would give you a different value of CV. They are irregular. They are Poisson-like irregular. That's the point. And I'm going to argue next week that actually it's interesting. It's interesting. It's interesting not only because there are questions about coding, interesting questions about coding, but it's interesting mechanistically. How it comes that these neurons are irregular, despite the fact that in slices they are pretty regular. You inject current, they fire very regularly, as we discussed on Sunday. Before we conclude, in 15 minutes there is going to be a talk that is given by Odelia Schwartz from Miami. You are all invited and encouraged to come. If you don't have anything more important to do, then please attend. I think it's going to be interesting.